welcome to the third session of the nonlinear least squares estimator lecture. And let's consider what happens when we have measurement error. So we can think of the true underlying model as a y star h x star, where the y star and x star are, you can think of it as the proper true quantities. And so if we think first of the error in the measurement of y star, where our measured y is actually equal to y star plus a measurement error eta, then we simply will have that y is equal to our h star plus epsilon, which is up here, plus our eta. And so we're fine if the expected value of eta is equal to 0 and if eta is independent of the derivatives of h. It would be the same as what we would say needs to be the case for epsilon. So, in fact, technically it has to be now independent of the difference of the two. So we are fine. Actually, the difference of the plus of the two here. This is a plus. If the expected value is not equal to 0, well, then we can just add a constant to the model. All right. And so then we would have a constant plus h with this term. Two things occur is if h already has an additive constant in it, then it will be that constant plus the mean alpha, so that you won't know whether you've got an actual constant associated with your model or a constant plus the mean of eta. So that would be the only caveat is if h actually has an additive constant already in it. Otherwise, we're pretty good with having measurement error in y. What about measurement error in x? Well, this is a little different story. So our actual measured x then is the true x plus this measurement error. And so constantly, what we would say is that we have y star, our true kind of y, is h at x minus delta, right? Because that was x star was what was in here, plus our usual error term. And if we use the mean value theorem to indicate that there exists an x now, an actual true x, or not true x, but a variable value, x tilde, between x minus delta and x, such that the derivative of h at that tilde is equal to the difference of h at x minus delta minus h at x divided by delta, then we can state that this h term, which is that term right there, we can rewrite, and we've got y star is equal to h at x theta plus the derivative times h at x tilde. Consider this kind of a whole new error term. So the problem then becomes whether or not that derivative is independent of epsilon. The derivative of this is independent of our epsilon star. Noting that the limit of epsilon star as delta goes to 0 is just epsilon, right? Because that's how we defined it. This goes to 0. As delta goes to 0, right? So as delta goes to 0, it's multiplicative. That goes to 0, and we're left with simply epsilon. So to look at this in a little different way in terms of misspecification in nonlinear least squares. Let's suppose that we have a probability space. We have variables y, x, and epsilon on that space such that y is equal to the function g of x plus epsilon. Let's suppose, however, instead that we are using a different model, and different model is that of H. And so let's define Q as being the difference of G at x theta naught, which is, say, the true actual mean, minus the function that we're considering. Take a difference squared. So if the error term is IID, expected value epsilon is 0, and the variance is sigma squared, if G and H are continuous on both x, the space of the random variable x, as well as the parameter space itself, if x and h are closed and bounded, which is a compact set, and these are these mathematical regularity conditions, you got to kind of go through these in order to get the results to hold. If Q is essentially dominated by an integral function, which is to say there exists a function m of x that's greater than or equal to Q, such that the function itself is integrable. In other words, the integral is finite. And finally, if theta star is the value that minimizes the integral of this difference across x, and if that is unique, or in other words, it's identified, there is a single value that minimizes that, which is to say the prediction mean squared error t, which we'll call capital T in this case. So we're minimizing that, and it is unique. There is one value that does so. Well, then it will turn out, and here I'm not going to go through the proofs, it will turn out that the p-lim of our estimator is theta star, and the p-lim of the variance is t. In other words, the theta star is going to be that value that minimizes the difference, and our estimator converges, in fact, to the value that minimizes that mean squared error of the associated with the difference between the two models. And we also get the idea that the variance of that estimator is the prediction mean squared error. So if we have y is equal to g again of epsilon independent of x actually independent, it's technically it's the derivatives of this with respect to theta, but it will pretty much say x at the moment. Keep that as a slight caveat on how I wrote this. Expected value of the error term equals 0, the variance is equal to sigma squared. And our model, however, is using h. So our, now I'm using parameters phi. Up here was theta naught. Here I'll use parameters phi. So our estimator phi hat is the value that minimizes the sum of squared errors associated with our model h. Y is equal to g. So let me plug that in there, g plus epsilon here. So we're minimizing g plus epsilon minus h transposed times g plus epsilon minus h. I switch it around. We're minimizing g minus h, kind of the difference between the two models, plus epsilon, the square of that, the sum of the square of that, in fact, which is the same thing as saying that we are minimizing the square difference between the two models, 2 times the error terms times the difference, and then the sum of squared error. C is not a function of phi, so we're not going to worry about that in terms of what we get when we minimize. And B is 0 because of the orthogonality of the error term. And so really what we have is phi hat is the argument of the differences between the models. So again, if the nonlinear least squares regularity conditions hold, then our p-lim of theta hat is equal to theta star, which is the value within the space of parameters that makes h the best model with respect to g, or the closest model to g. In other words, H may not be the correct model, but our estimator is the estimator that makes that model as close in terms of the sum of squared errors as it could be to the true model. And our p-lim of this quantity is variance squared. Okay. Now we'll go one more time and look at it from a slightly different perspective. If we again define our Q as this differences between the true and the model I'm using, and it's the sum squared of those differences. Also, I'm going to define as A the expected value of the second derivative, B as the expected value of the outer product, and let me put a few our usual mathematical niceties have to be there. Q is differentiable first and second with respect to theta. Both the derivative and the second derivative are well behaved, dominated by the integral function of x. You can also say that this one does not fly out of whack as n goes to infinity also, but really here we're just talking about both of these are behaved in terms of being dominated by an integral function of x. Our theta star is an interior point of the parameter space, and the A and B, as I defined above, are non-singular, so they don't degenerate into like a zero. You could think of their nice matrices. Then the theta hat minus the theta star, which is the true value that makes the model closest to the actual model, converges to a normal zero of a certain function of theta star, and that function is the A theta star inverse, B A theta star inverse. This is our sandwich estimator that we've seen before. So we are looking at the, think of this as a Hessian type matrix, right? It's the second derivatives. So we've got the second derivatives times inverted times the outer product of the first derivatives. It's the sample average of each of these for an estimator times this again inverted. And this can be estimated by using again the sample estimates of each of those quantities. Okay, so this is all well and good. This is basically saying that if we have the wrong model, we at least have the best wrong model. Not sure exactly how that is comforting in some respects, because it means that your estimator of a wrong model is, of course, not a consistent estimate of the true model. It's not necessarily so. It is a consistent estimate of the best parameter value that would make your model closest to the true model. So some might say, well, since it's not a consistent estimate of the true model, then I guess it's not a consistent estimator. And I guess that's true. On the other hand, we can consider that perhaps in many cases there is no actual model. A model is just that, a model, and therefore it is hard to say what G would even be that there would even be a G that exists. But nonetheless, this is helpful to know that at least the non-least squares estimator, as well as the maximum likelihood estimator, misspecified models at least gets us as close to the underlying true model, assuming it exists, as we can asymptotically. All right, now let's look at a slightly different situation. This is going to go into least squared simulated errors. And your readings has a manuscript on it that you can read. So we have how to estimate a general model is kind of the topic of using least squared simulated errors. And by this I mean that let's say y is equal to some function of our observed random variables, unobserved random variables, and then our parameters. Now, our regression in general is y is equal to the expected value of y given x plus some error term. In this case, the expected value of y given x is the integral of this function with respect to the distribution of the unmeasured quantities, which in this case is eta. So if we plug this up into here, we have y is equal to this integral plus eta. If there is no closed form to the integral, doesn't mean that we have to stop. We can use numeric approximations to the integral, and in our case, for this class, we will use Monte Carlo integration. And so we will get a Monte Carlo estimate of the expected value, which is a theta, I get my little hat here, and the least squares simulated errors estimator, in a general form, is the parameter that minimizes the residual that's associated with y minus this estimated expected value, which you use Monte Carlo integration to estimate, transpose times a weight matrix times this quantity over here. So it is a sum of squared errors, but they're simulated errors. This is a simulated error because this quantity here is simulated. The asymptotic properties of this estimator is that it basically follows that it is a nonlinear least squares estimator plus an error term. And it turns out that the error term goes to 0 asymptotically. And so essentially we get that the nonlinear least squared simulated errors estimator is consistent if both n and r is the number of Monte Carlo draws, and n is our sample. So as both the sample size and the number of Monte Carlo draws used to calculate our integrals rise both to infinity, at any rate, the nonlinear least squares simulated estimator is consistent. It's consistent if they both rise at any rate, and if the underlying nonlinear least squares estimator is consistent. In other words, if for the underlying actual expected values, if we actually had the true expected values and we're not simulating them, if the nonlinear least squares estimator is consistent. So all of the regularity conditions that we apply to the nonlinear least squares estimator would need to apply here, and then we're just replacing the expected value with an estimate of the expected value based on Monte Carlo simulation, in which case as both n and r rise to infinity, we have a consistent estimator. It is also asymptotically normal if it's consistent, and if the number of Monte Carlo draws is rising faster than the square root of the sample size. Write it this way, is that if the limit is n and r going to infinity, if the square root of n divided by r is going to 0. Now here's an interesting question, and that is that you never are actually in a race. You don't have a sample size and a number of Monte Carlo draws, and off they go, and the number of Monte Carlo draws is going faster, increasing faster than the square root of n is increasing. It doesn't happen. You pick values, and because of that, it is unclear from the mathematics what these asymptotic properties really mean. So you really need to look at the properties of the model for any given situation. And you do that by Monte Carlo experiments with the model and by bootstrapping the model to investigate the properties of the estimator for a given model that you have and for a given sample size that you have. So this is key, is that you need to investigate your model a bit to see if you're happy with the kinds of results that it would return. And by that I mean you create, in the Monte Carlo sense, you create a parallel world in your computer that has parameter values that you know that they are because you set them that way. You generate you generate data based on those parameters, and then you run your model in nonlinear least squares simulated errors and see if you recover those estimators. You do that a number of times because you want to get a distribution and see how biased it is, whether the center distribution is lining up with the true values. Also, you got to remember something about heteroscedasticity. The fact that you may specify that let's see, we'll go to here. You may specify that eta, which is a unobserved random variable, is homoscedastic. It has the same variance for all the observations in the data set. Because it's filtered through this nonlinear function of x, doesn't therefore mean that in your regression equation, the regression error over here is homoscedastic. That doesn't mean that. This may still be heteroscedastic, so you need to evaluate the regression error for heteroscedasticity regardless of the fact that you have specified the unobserved variable in the function g as being homoscedastic. Just a reminder. They are separate issues. So let's take a quick example, and let's look at, let's suppose that for all kind of individuals in a population, that their relationship between their values of w and x is expressed this way, right? And the way that you can think of it as, here is the y-x relationship. Here is a straight line that is simply x beta, and for each person in the data set, they have it bent to a certain amount according to their own individual delta. So this delta, when we apply it to a probability space, is a random variable, and let's suppose for the moment the random variable has a beta distribution. In other words, delta goes between 0 and 1, which is what I had mentioned up here. So what we have is y is equal to beta xi to the delta. So we're not going to specify a regression function explicitly. And here we have delta I itself has a distribution. It's a beta distribution, but delta I is equal to log yi divided by log beta times xi. And this would require that because this delta I goes between 0 and 1, this would require that beta x is not equal to 1 for all x and for all beta. And beta x is greater than y, that would need to be the case as well for all x, y, and beta. And this is hard to implement these constraints in Stata to be able to estimate this as a maximum likelihood based on the deltas distribution. It would have to search these values and not violate these conditions. But we can express this as y is equal to the integral of this plus my regression error here. And so we can evaluate this integral by drawing from the distribution of delta, evaluating this quantity at each of those draws, and taking the sample average. This is the Monte Carlo integration we did in the Monte Carlo lectures. And we take the average of these by estimating that integral, 1 over r, the summation of beta x delta r, and that gives you an estimate for any given x value in the data set. Embedding that into our least squared errors estimator, and that gives you the least squared simulated errors. You can do this by using Stata's nonlinear command, and you embed in the program that is going to provide Stata with the expected value associated with each person in the observation. You embed a Monte Carlo routine to get an estimated expected value for each observation. And because all that Stata cares about is that it has a variable that it generated that gave the expected value. And then it's going to minimize the sum of squared errors based on that expected value. So similar to maximum likelihood, you can embed Monte Carlo integration routines within the programs that you might use for Stata's nonlinear command. So this is the end of the nonlinear least squares lecture. Do be sure to read the readings, and then in class we will go over examples with regard to how to program and evaluate the nonlinear least squares models.